Source transformation. Source transformation is a tool to make our analysis easier. Node voltage or mesh current equations can be attained by inspection when the sources are all independent current or independent voltages. A source transformation is the process of replacing a voltage source in series with a resistor with a current source that is in parallel with a resistor, or vice versa. And so graphically, this is what it is. I have a voltage source called Vs, and it's in series with R. And here I have a current source Is, which is in parallel with R. And how do we, if I know this voltage and this resistance, I can calculate what this current will be. If I know what this current and resistance is, I can calculate what that voltage. And this will be leading up to the Norton and Thevenin equivalence. This is best shown, of course, with an example. This is the example in the book, but I have changed the numbers so that you can have another example to follow. And I've run it in LT Spice to see that, yes, it's 2.89 volts coming off of V out. I have a voltage supply, positive to negative, and I have a current supply forcing current this way. And I have these resistors. So first thing we're going to do is notice that this can be turned into a current source because I have a voltage and that looks like it's in series. And I'll calculate that new current source. It's 3 volts divided by 10, or 0.3 amps. And now I have this. And notice that this node voltage 1 is now shorted to out, and so there's no node voltage 1 anymore. When I reran the simulation, notice it's still the same. V out is the same. Now we can continue along with this is by noticing that this resistance and that current source are in parallel, and we can turn that into a voltage source. So V equals IR. There's my current. There's my R. It's 10 mega ohms. 10 milliamps times 1 meg. That's 10,000 volts in series with 1 meg. Notice we're still getting the same voltage. Then we notice that we can combine these two resistances to 1.01 meg. We're still getting the same voltage across V out. And we notice again that we can convert this back to a current source. So now Is equals Vs divided by R. That's 10,000 divided by 1.01 mega ohms, or 0.0099 amps. So now we're back here. We notice that R1 and R4 are in parallel, and so we combine them into R4, which is almost 10 ohms, and you'd expect that for 10 being so much less than 1.01 mega ohms. And then we notice that these current sources, if I redraw it, one's over here, one's over there, but they each have one terminal on that is connected to the same potential, so they're in parallel. So that current coming out of here is the sum. One's positive, one's negative, so I just have to subtract this from that. I get 0.29 volts. Now I have this, and now it's very simple current division. I have the current that I want, that I have. And it turns out the current is 0.289 milliamps. So I multiply this current times R4 divided by the sum of R4 and R3. That's current division. And then the voltage is simply that current times R3. And I get 2.89 volts, which is what we achieved in LT Spice at the beginning of the presentation.